All right, everybody. So here, time for trig substitution part 2. So I just made the video for part 1, and I just here want to go, as I would normally do from one video to the next, just a little bit deeper into the process. Okay? Now, one thing that we need to do is figure out what the substitution should be. In the last video, I gave you a problem, and I told you it was trig substitution, and I gave you the substitutions just to see how it worked out. All right? So now we'll talk about, well, how do you figure out what the substitution should be? Now, before I do that, though, it first comes down to the fact that this is not a problem that we can work by u substitution or some other method that we already know. It's a new problem. All right, so say that we can come to the conclusion one way or another that this is trig substitution. Then how are we going to do it? Here are the guidelines, okay? It depends on whether the integral contains a difference or a sum of squares. So in my notation here, a is a constant, and x is the variable that's involved in the integration, okay? So it will have a difference of squares, a squared minus x squared, or we'll have a sum of squares, a squared plus x squared. And then we decide on our substitution based on which one of those we have. So let's pick this one out first from the cases. That says 100 minus x squared. Is it true that the integral contains a difference of squares? I say, yeah, that is the problem I have. And then it says that we substitute x is a sine theta in that case, where the number a is a constant depending on what that number right there is. All right? So I think that we have it for this one. Let me write something down. Okay? So my integral contains, to use the same wording that I had there on my other paper, a squared minus x squared in the form of 100 minus x squared. I know that it has other stuff. I know it has that 3 over 2 power, and I know there's a 1 up there, but it just says the integral contains a difference of squares, and there's my difference of squares. It's 100 minus x squared. So what would that make the number a, the constant a? That would be 10, all right? Okay, so there, we've got it. We've at least made an initial inspection of the problem to decide what to do. So what does it say to do then? It says then that we will substitute a sine theta. X is a sine theta. All right, so then we will do that. Here is our substitution. Our substitution that is recommended for this problem is that x is 10 times sine theta. All right, so we will substitute that for the x. Now, all right, that will take care of the x. What about the dx, the differential? That also has to be substituted, but we always get that the same way. Once we decide on the substitution of x in terms of theta, or x in terms of u, if it's u substitution somehow, then we can find how the differential substitutes. So dx is going to be 10 cosine theta d theta. And that's the substitution that we're working with this time. All right? Okay. So let's go ahead then and see where this takes us. All right? So if I substitute accordingly to what I've determined over there, then I will get this 1 over 100 minus, okay, so x is 10 sine theta. Okay, and I'm going to square that, but then this entire expression under the bar there gets the power 3 over 2. And then the dx, that's going to substitute as 10 cosine theta d theta. Okay. And then the substitution has been made. All right. Okay. Now this will always need, I hate to say always, but pretty sure that always is the correct word. Always needs some cleaning up, okay? So I'll do a few things to it, all right? First, I'll see that, when we create our substitution and we involve the differentials, 10 times cosine theta times d theta is what you get, but it's not like they're all stuck together, of course. I mean, they're all multiplied together, but we'll leave the differential out there. Let's put the 10 here on top and the cosine theta, because that's like a fraction over 1, and if you multiply it by this fraction, it puts the 10 and the cosine up there. And it'll leave me the differential over here, okay? And then down here, I'll get 100, okay, minus 100 if I distribute this square to those factors. Sine squared theta, okay. And then that is getting the power 3 over 2 at some point. Now, let's see from here. What can I do from here? Here's what I noticed about this, okay? I want to do some simplifying on that part, but I don't want to rewrite the whole problem just to simplify the bottom part. So here's what I'm going to do. I told you in the last video that normally when we're working with trig functions, we can expect to use some identities to come into play at some point. And in this method of trig substitution, like the same two identities always come into play. All right? Like you see that sine squared? You can almost see that there's a 1 minus sine squared there. Yes, that identity will come into play every time you use the sign substitution. Okay? So what I want to do is this. For just that part right there, just the part inside this parentheses that gets that power 3 over 2, I would like to factor out 100, okay, and leave myself with 1 minus sine squared theta, okay? So can you agree with my factoring? You probably can't agree with my factoring. So what about next? Oh, there's that identity I mentioned. So 1 minus sine squared theta. You can expect to see that in these problems. In the problems that involve a substitution of sign, that identity will show up, okay? So, well, what is that? What is 1 minus sine squared? That's cosine squared. So 100 cosine squared theta. Okay, so what you're really looking at in that parentheses there that gets that 3 over 2 power is 100 cosine squared. Okay, so let's now update this thing with that. All right, so here I'm going to get still my 10 cosine theta up there. And here I'll have 100 cosine squared theta. Right? Okay, 3 over 2 power. Now, exponents distribute across multiplication, you could say. So this is 100 to the 3 over 2 power, and then cosine squared to the 3 over 2 power. And I thought that we would look at those separately, all right? And I don't want to clutter up the work that I have here too much. So let's just say, like, okay, if we need to do some work off to the side, I'll get this, 100, 3 over 2 power. And then I'll get, cosine squared, which already has an exponent, right, to the 3 over 2 power. All right? Now, so this, I think most normal people do that by calculator, but the way it works is it's the square root of 100, which is 10 to the third power, which is 1,000. So I'm going to get 1,000 right there. And in this case, when we raise a power to a subsequent power, then we multiply them together. So I'm going to get cosine to the third power theta. That's what that's going to amount to down there, that part. Okay, so okay, now I'm going to add that into my next step. All right. So now we're looking at 10 on top, cosine theta. And then I said I had 1,000, okay, cosine to the third power theta, d theta. So that's how it worked out, right? Now, obviously we expect to get somewhere at some point, right? That would be the obvious objective. And it is at least getting simpler, but I've got to get it to a point where I'm looking at it and I know I actually know what the antiderivative is, okay? So I'll do a few things that I think will get me to that point. I think I'm just 2 steps away. I got 10 over 1,000, so that's going to be 1 over 100, which is a constant that I will remove from the integral. And I guess between the cosine and the cosine to the 3rd power, I'm left with cosine squared. Okay? All right. Now, it is getting pretty simple. There's not much more I can do to simplify it, but I still, I've got to get it to where I know the answer. You know, like if I saw that it was something and I knew the antiderivative of it, that would be success, okay? So I notice this and I think, oh, well, you know, I don't know what the way it is, but can I turn the cosine squared into something else? Well, we're working with trig functions, and trig identities are, like I said, is going to come into play. So I think what I should do is put this as secant squared. And then that does it for me. This is the point where I wanted to get. Do you know something that if you took the derivative of it, you would get secant squared? Is there such a thing? And it is tangent, right? So my answer, 1 over 100, tangent theta plus c. Okay, yes, it is true. The derivative of tangent is secant squared. All right, so that's what we were hoping for, right? To get it to that point. Work to get to that point, but we got there. Now, what could come next is that I want to put my answer, generally, in terms of the variable that I started with, okay? And so we want to do that here. So I need to find some way to get theta, the theta that's right there, in terms of x. I need this to be in terms of x, okay? All right, here's how we do that, all right? I guess there are different ways you could do this next part, but I'll show you what I think is probably the most agreeable way. So let's go back to what we were working with. Where's the link between theta and x? Where did it all begin? It all began right here. That's the link between theta and x. This must hold the key to figuring out how to put this back in terms of x, because this is where it all started. So from this, I'll say that if x is 10 sine theta, then I could say that sine theta was x over 10. Okay? All right, so just bear with me. You're probably not going to, if you've never done this before, you don't know where this is going yet. But don't worry about it, all right? I'll show you, and it's something that we'll practice. Okay, so sine theta is x over 10. Now theta, what's theta? Theta is an angle. And so an angle is something that you could visualize if it would help you. So why don't we do this? We can think about it this way. Say that's theta. Being an angle, it's something that is tangible. I can look at it. I can draw it if I want to. What would this angle be like if the sine of that angle was x over 10? Well, say I put a right triangle right there. The sine of an angle in a right triangle is the opposite side over the hypotenuse, so this would be x, and this would be 10. Okay? All right. Now, could you figure out this side? And you might say, well, okay, where are we going? I'm dying to know. Well, see theta right there? It's that angle. If you can tell me the tangent of that angle, then that's your way to get this back in terms of x, x being the variable that you started with. If you knew this side down here, this base right here, then you'd be able to do it, because tangent of an angle in a right triangle is opposite over adjacent. It's like you just figure that out. So we use the Pythagorean theorem. This side squared plus this side squared is equal to that side squared. That will make this bottom side down here, this base, that will make it 100 minus x squared. Okay, And by the Pythagorean theorem then, a squared plus b squared is equal to c squared. Okay? All right, so I have it now. I'm going to say for this part right here, where I resubstitute my original variable back, very important, C triangle. You know, that triangle right there, that's our reference for doing this. I'll get 1 over 100 times the tangent of this angle, which is x over root 100 minus x squared. So 1 over 100, x over root 100 minus x squared. And then plus c. All right. So we could leave it like that if you want to. When you're putting stuff in online homework, if that's what you're doing, you know, they can be more or less picky about what the answer is actually typed into B. So, you know, maybe we'll put it all as one fraction. Like we can multiply those together. We get x on top, we get 100, and then times root 100 minus x squared plus c. Okay. And then let's say, well, all right, finally done. Okay. Now this one, it took me just about the entire paper. And that would be normal for these. I mean, if I'm showing my work, I mean, if I'm doing stuff in my head, it's not going to take me that long. But, you know, I did say that these problems would be more lengthy than the ones that we're used to, right? There's lots of little things to know. You got to know some algebra. You need to see trig identities when they're relevant. You got to get all the way down to here and remember that tangent's what you want, the derivative of tangent, secant squared, and so on. Right? Those are all the keys to the problem. Now, okay, the idea from here would be practice. Okay? So let's do this. Let's try another one. Okay? And I wanted to, for right now, I want to do one of each case. So let me get my paper out with the cases. So say we have this problem right here. We want to do this one. Now this one, like I have to say that you could do this one by u substitution. Okay? Just to be honest with you, if you let u be 49 plus x squared, then du is going to be 2x dx. You got the x dx right there. Okay? So, all right, yes, and so you might say, well, why is it in this video if you can do it by u substitution? And I wanted one to practice, all right? And who knows, like if you get in the habit of doing the problems this way on an assignment, you might gloss right over the u substitution, not even notice it. But for now, it's an example. You can work it, you can practice it. That's what I need to do at this point. So I look at this problem, and I just want to see how it fits in here. That the integral contains either a difference of squares or a sum of squares. This one contains a sum of squares, right? Okay, all right. And so let's say, put it down that way. That the integral contains a squared plus x squared. It contains a sum of squares in the form of 49 plus x squared. Okay? All right. So yes, it has a sum of squares. Now, is there other stuff also? Yeah, there's the x and the 7 and the root, and that's not part of it. It says if the integral contains. This statement doesn't say if the only thing in the integral is obviously not what it says. It'll have other elements to it. Okay? So what does that mean? It means that a is equal to 7. All right, the constant right there, a is equal to 7. And what does that mean that we do? It means that we substitute a tangent theta. All right, if the integral contains a sum of squares like so, there's your substitution that's recommended. All right, so here we go. Let's say we're going to sub as a result, x is 7 tangent theta. Okay? So that's how we'll substitute the x. What about the differential dx? We'll take care of that the same way we would with any substitution. Dx will be 7, and then this will be secant squared theta d theta. So I'll substitute the x and the differential dx and put everything in terms of this new variable theta. I'll get stuff with theta in it and d theta. Okay? All right, so say I make that substitution. I'll do something in addition to that this time. That 7 is kind of bothering me right there. I'm trying to think, should I leave it there or not? I guess I'll leave it there. I actually think that it might be better to leave it there. So let's see, x, 7 tangent theta. Okay. Okay, over 7. Oh, yeah, see, 7. Okay. And then here, root 49 plus x squared. So 49 plus the x is 7 tangent theta. Now at this point, like you know that I could write the x there and put in parentheses and put the square and so on. But it's just that this is going to get squared when you put it in. It's going to say parentheses 7 tangent theta squared. So that'll be 49 because that's what 7 squared is. And then tangent squared theta. Okay? All right. So anyway, I got that part in. That's all the x's. And what about the dx? 7 secant squared d theta. So then times 7 secant squared theta d theta. Okay, so now it's all been done. It was in terms of x and the differential dx. Now it's in terms of theta and the differential d theta. What can we do with that? Okay, so let's look at it like one little piece at a time. No, we try not to do too much. Let's see. So the 7's cancel, and I get tangent theta. All right. And I don't need to keep this 7 secant squared. It's not attached to the differential. It's all multiplied. So I'm going to do this. I canceled those 7's, and this one I'm going to go ahead and remove. Okay. Because it's a constant, I can do that. And let me put that like secant squared over here in front of the root. Okay, so here I'm just reorganizing a little bit, not doing anything real big. And I still got this 49 plus 49 tangent squared theta. Okay, and then the differential d theta. Now what can I do next? Now I had mentioned before that you can expect to use like certain identities, okay, every single time. There's one right here. 1 plus tangent squared is secant squared. I don't quite have 1 plus tangent squared. Okay, I've got 49 plus 49 tangent squared, but I can factor out the 49 and get 1 plus tangent squared theta. All right, and then 1 plus tangent squared is secant squared. So I'm looking at 49 secant squared theta. Okay, so that's really what's sitting under that root right there. So let's reevaluate it that way. Okay, so I got my 7. I've got tangent theta, secant squared theta. Now I got this root. I know it's still like you're wondering, why do I write the lines with, oh, I just want, you know, I think math should be neat. It's easier to follow that way. So, plus I've got a problem where I need to do that, or it bothers me if I don't. So, 49 secant squared. Okay. Now, what can we do here? Well, the roots can be applied across multiplication. So, it's going to be root 49 times root secant squared. So, okay, so it's coming together then. I'm going to get 7 tangent theta secant squared theta, and then this will give me a 7 root 49, and root secant squared is secant. There's a little bit of fine print to that, but we can say that the square root of secant squared is secant. Okay, so don't worry too much about it, although there is some fine print I'm not mentioning. All right, so let's see, we got it. Let's see if we can rearrange a little bit. Okay, so how about this? I gotta think of a way to do this. That's the whole idea, right? Is I gotta get to a point where I see something I recognize. And you know, I'm not there yet, but that's what I'm trying to do. Okay, so how could I rearrange this so that I can work it? The 7 just doesn't appear to have any relevance, so I'll go ahead and move that. I got a 49 now. But I think that I could do something like this, that what's the derivative of secant? Secant tangent. So what if I did this? What if I said secant to the 3rd power, secant squared theta, and then secant tangent. So that's just all I'm doing is rearranging a little bit, and I'm putting a parentheses here just to highlight my separation. There's no mathematical significance to that parentheses really, but I want you to see that I got secant squared and secant tangent. Everything is still there, it's just rearranged a little bit. What kind of problem is this? This is u substitution. Okay. The derivative of secant is secant tangent. So here's what you'll find is that this is u sub, when we get to this point, u will be secant theta, du will be secant times tangent. Okay, so that part right there is u substitution, and it's going to look like u squared du once you get that. All right. Okay, so let's say then that here's how it works out from there. I'll get my 49. I'll get secant to the 3rd power theta over 3, okay? Because it's going to be u squared du, and I'm going to get u to the 3rd power over 3, and then I'm going to resubstitute, and then I get my constant of integration. All right. So let's see, one more thing. Let's just say 49 thirds to group the constants together, times secant to the 3rd power. Plus c. Okay, and then like we've mostly done at this point, that's the antiderivative. When I got here, I could find the antiderivative, the ultimate goal of the problem to start with, right? Okay, now at this point, like I hope you can predict the next part of it. The next part is to put this antiderivative back in terms of the original variable, whatever that is, and that was x in this case. All right, so can we put the theta there in terms of the x? Now, you just saw me do another problem where I told you that the key to getting x back in this goes back to the origin of the link between x and theta. It's going to start with that. If you say x is 7 tangent theta, that's how you could substitute one for the other. That's how we'll get the x back. Okay? So let's take this and analyze it the same way, and we're going to use the triangle like the last problem. All right? So let's say this. If x is equal to 7 tangent theta, for me to explore the link between the variable x and the variable theta, then I could say that tangent of theta was x divided by 7. Okay? So that's just a little bit of algebra. But then I could say that theta, what kind of a thing is theta? Well, theta is an angle. And so we could see an angle. Right? We could visualize the angle. What's this angle theta look like if the tangent of this angle is x over 7? Well, in general, tangent of an angle in a right triangle is opposite over adjacent. So this will be x, this will be 7. And then I want the secant of that to the 3rd power. So theta, see the theta right there? Here it is. What's the secant of that? Well, secant is hypotenuse over adjacent. It's the reciprocal of cosine. All right. So I need to know this side right here. I need to complete the triangle. And so I can use the Pythagorean theorem to do that. And this side will be 49 plus x squared. Okay. All right. And you might think, is it always exactly this part? No, but it does involve that sum of squares. Okay, it might not be identical to this. And in the last problem that we did, it wasn't identical, but it will involve the sum or difference of squares that you're working with. Okay, so I think I've got it then. Let's put a little note here that secant of theta, you see that angle right there? So I said that would be the hypotenuse, which is root 49 plus x squared over 7. Okay? Now, so I want then secant to the third power. I know what secant is. I put it in terms of x. All by my original link between x and theta, a triangle, and a little bit of trigonometry. All right? So here goes. Let's do like this. We got a 49 over 3, okay? And I'm going to put secant to the third power. You see? The order of operations is when we write the power like that is secant of the angle, whatever that is, to the third power. Secant of the angle was found to be this. So let's see, 49 root plus x squared over 7 plus c. Okay. And then we mostly got it. You're probably like, this thing's got to come to an end at some point. We're almost there. So 2 things real quick. Let's see. So that's 3. That's like 7 times, like 7 to the third power. That's like 7 times 49. We're going to cancel the 49. So let's do this. I'm going to get 1... Well, how about, I don't want to do too many steps at once. It's tempting, but let's see. So take this. What happens when you raise this to the third power? Okay, so I try to do a little bit of reviewing when I do the videos. It's hard to decide how much is appropriate, but let's say that we're looking at this, right? Can you agree with that top part there? Root, that's 1/2 power, 49 plus x squared. That's to the third power. So we're taking something, raising it to a power, and then raising it to a subsequent power. And you multiply the powers when you do that. So what this would be is 49 plus x squared to the 3 times 1/2 power. That's 3 over 2. So I'm going to write 49 plus x squared to the 3 over 2 power. That's what happens when I apply this exponent to the numerator. Okay, to the denominator, I'll get 343. For canceling purposes, I was thinking of it like it's going to be 7 times 49. Cancel the 49. So here's what I end up getting. If you cancel 49 with 343, you'll get a 1 and a 7. Okay, 1 and 7. So you get 21 right there. So let's say 1 over 21 times 49 plus x squared to the 3 over 2 power plus c. Okay, then we've got it. All right? We got it. Different problem. Some of the steps were different than the one I showed you just before this. If you can even remember that long ago. Yes, I did show you a problem before I did this one. Some of the steps were a little bit different, but it still involves what? Like trig identities like that one. Okay? Every time that we use this substitution for tangent, x is a tangent theta, you can expect to use that identity, 1 plus tangent squared is secant squared. Just go into the problem thinking that, all right? Because that's what's going to happen. But, you know, there's the triangle also. Our original substitution gives us the triangle, gives us a way to resubstitute the x, and so on. All right, so we did that one. Now I need to discuss something that it needs to come up at some point in calculus too. And what about integration limits when you're dealing with substitutions? This is not just trig substitution. This would be anytime you're dealing with a substitution. Because some people could take issue with this. They would say, can you leave your answer in that form right there? Do you have to resubstitute the x back from the theta? And I'd say, well, no, you don't have to, but it depends on what you're doing. So let's say that we encounter a problem like this. It's a definite integral. The definite integral from 0 to root 15 x over 7 root 49 plus x squared dx. That's the problem we just did. So there are two ways that you could do that, all right? You can take the antiderivative that we found when we just did the problem, which is this, and put the bounds in. Put root 15 in, you get 64, you get 49 if you put 0 in, and just do the math, all right? You'll get 169 over 21 if you want a decimal, 8.0476. But when we work with substitutions, you don't actually have to change back to the original variable if it's a definite integral, okay? So here's what I mean. Say this original problem has bounds of 0 to root 15 when the variable is x, okay? Suppose that you use a substitution to work it, but you don't want to go through all the extra steps of getting the x back, right? Can you do the integral with theta? Well, as long as you change the bounds to theta, okay? The bounds here are x, right? The variable's x. So what's the 49 over 3 there? Where'd that come from? Well, that was the antiderivative that I got before I got the x back through the substitution. So see, 49 over 3 secant third x. Say like somebody could say, I'm just going to leave it that way. I'm not going to bother with all this other stuff. But I need my bounds to be in terms of theta. Okay? So, all right, well, again, what was the link between x and theta? That's how you're going to change your bounds there if they need to be in theta. Well, we got that answer from the substitution that x was 7 tangent theta. So suppose x is 0. What does that mean for theta by way of this substitution? If you put 0 for the x in the substitution and you solve for the theta, you'll get the theta 0. So the bound x being 0 equates to the bound theta also being 0. All right? Now, what about that upper bound right here? X is equal to root 15. Okay, so we could do it the same way, though. If x is root 15, right there, that gives me a way to find theta. Root 15 equals 7 tangent theta. So I divide it by 7, and I use the inverse tangent function, okay? So if x is root 15, theta is tangent inverse of root 15 over 7. That's what that bound should be, if your variable is theta, right? And we're going to leave it like that. So that's how we got to change our bounds. Now, definitely, with a calculator, I did this. And in my calculator that I happen to have with me right now, it will do this and give me exact fractions, okay? If your calculator won't, then you can just verify that you get that decimal. Don't worry about it. I believe the problems that you'll see anyway say to round the answer. But when I did this with my calculator, that's what I got, and then I subtracted and got 169 over 21. I got the same answer, of course, right? You get the same answer. It's just a matter of, if you were doing a definite integral, do you want to go through the trouble of changing back to the original variable, x, and then substitute the original bounds? Or would you like to just leave the antiderivative in terms of theta and adjust what the numbers for the bound should be? Okay? So that's, I guess, a decision up to everybody at this point. But now you see how you do it. From the substitution, given the x's, you can find the thetas. All right? Okay. So that's an additional detail that everybody should know about and be aware of. And let me see. So if it's not a definite integral, then I do want you to change it back. All right. If it's not a definite integral, make the substitution, solve the antiderivative, which will be in terms of theta. Through your original substitution, figure out how to get x back in and give me the answer in terms of x, the variable that you started with. Okay? All right. So let's see. Are there some exceptions to using the triangle? Do you use the triangle every time to do this? The answer is no, you don't use the triangle every single time. Here's the very first problem I showed you in part 1, when I made the part 1 video. And I don't want to rehash everything that we did, but when I worked it, I got all the way back here and to there. And I said I need to put theta back in terms of x. And all I had to do was say, well, if the substitution was x was half tangent theta, then I can solve directly for the theta, and it says theta is equal to tangent inverse 2x, and so in place of the theta, I put tangent inverse 2x, okay? So yeah, in that case, if you just get theta, then you use the inverse function to put theta back in terms of x. If you have something like, you know, tangent theta, secant theta, sine theta, cosine theta, whatever, you know, function of theta, then we'll look at the triangle. Okay, but it plays out in slightly different ways with every problem. You know, like it or not, you probably just have to practice it.